Every time you log into your bank or send a private message, your browser displays a tiny padlock icon. We see that symbol, and we immediately assume our data is completely safe from the outside world. But most of us have a very narrow idea of what that safety actually means. We tend to think of encryption as a simple digital shredder, taking our sensitive information and scrambling it into an unreadable mess to hide it from anyone trying to eavesdrop. Here's the hidden vulnerability. An attacker sitting between you and your destination might not care about reading your message. Their goal might be to silently corrupt your data or subtly alter the numbers in a financial transaction while the package is still in transit. If a hacker intercepts a scrambled message, maliciously alters the contents, and forwards it along, the receiving server has no idea it's been compromised. It will obediently unlock and process the corrupted payload. Privacy is only half the battle. If you can't definitively prove the data hasn't been tampered with, that privacy offers a false sense of security. You're guarding a message that might have already been turned against you. Modern internet security requires a two-part solution. We need a system that simultaneously locks the data away from prying eyes, while also providing mathematically undeniable proof that the package arrived exactly as it was sent. And because the global internet moves massive amounts of information constantly, this verification process must happen in milliseconds. Any delay would completely crash network speeds. The digital world urgently needed an algorithmic solution that could act as both an unbreakable vault and an instantaneous tamper-evident seal. The solution that fills this vacuum is AES-GCM. It falls under a unique cryptographic category called AEAD, Authenticated Encryption with Associated Data. The first component, AES, provides the globally trusted muscle. It handles the heavy mathematical lifting, rapidly scrambling the raw data to ensure absolute secrecy. The second component is GCM, or Galois Counter Mode. This is the mechanism that works alongside the encryption process to solve the tampering problem. As the data scrambles, GCM generates a GMAC, a Galois Message Authentication Code. Think of this as a highly complex digital wax seal that attaches itself to that specific packet of data as a unique tag. The math linking the data in the tag is extremely fragile by design. If an attacker alters even a single bit of the encrypted payload during transit, the unique tag mathematically breaks upon arrival, triggering an immediate rejection. AES-GCM addresses the internet's vulnerability by ensuring that any tampered data is recognized and discarded before it can be processed. At first glance, performing two highly complex mathematical operations, encrypting the text and hashing the seal, at the exact same time seems like it would create a massive bottleneck for web traffic. The mechanism that overcomes this bottleneck sits inside the devices we use every day. Modern computer processors are physically engineered to support AES-GCM directly at the hardware level. Instead of relying entirely on software to calculate these complex equations, the CPU itself takes on the heavy lifting of the encryption algorithm. By bypassing clunky software limitations and processing the math right on the silicon, this direct hardware support accelerates the dual process to high speeds. The combination of mathematical logic and direct physical hardware acceleration elevates AES-GCM from a clever theory into a highly efficient, everyday utility. This balance of strength, integrity verification, and hardware-accelerated speed caught the immediate attention of global cybersecurity authorities. It was officially validated and adopted by NIST, the National Institute of Standards and Technology, as a definitive global standard for modern cryptography. Following that validation, it was integrated into the core structure of universal Internet protocols, most notably serving as the backbone for TLS, the protocol that secures your network communications. By achieving this standard, AES-GCM essentially became the foundational code for establishing trust across the entire Internet, which brings us back to your daily routine. Every banking transfer, your private messages, and secure web searches rely on this specific algorithm. The feeling of safety we get online comes from these algorithms actively verifying every packet. This is a continuous, high-speed mathematical check happening in the background of every click. AES-GCM functions as a foundational engine of the Internet, processing the mathematics of both secrecy and proof at the speed of light to maintain the integrity of our digital world.